Okay, so we're going to be looking now at example three. Now, as we look at example three, what we have is we have a single link number two. I just kind of used my highlighter. I colored it in just so you could see it was a single link. It's shaped like a triangle and it has points B and C, and then its center of rotation is going to be at A, which is going to be fixed at the frame. Okay, so you'll notice here that we've got our frame symbol. This is link number one, and then we've got our link number two, which is going to be this triangle ABC. Additionally, we have some lengths from the center of rotation out to each one of the points, and then the distance between points C and B. Now, it's telling us in the problem, the link above rotates at 15 RPMs clockwise, and they want us to determine the items that are here. Okay, so based on that information, we just want to kind of show an arc pointing in a clockwise direction, and this is going to be W2 is equal to 15 RPMs, right? Okay. Now, what you're going to do is with that information and the information that you see on here, you are going to fill in what you believe all these values should be. Now, the W's shouldn't have to calculate anything. Okay, you're just going to either put 15 RPM or zero, depending on the point or the item that it's asking for. But for the V's here, you're going to want to do the calculation. So the calculation is going to be from our first page, okay? And that is V, straight line velocity, is equal to angular velocity times R, or its distance away from its center of rotation. So I'm just going to put that value up here. V is equal to WR, okay? Now what I'm going to do is I'm going to give you, I don't know, 5 minutes-ish to just kind of get started on this and fill in some things. If you're not sure, leave it blank. We're going to talk through each one of these, okay? But I just want to give you a chance to kind of put your thoughts down, okay? Mhm. And I don't want anybody to think that I'm expecting them to put something for everything. If you're unsure, just go to the next one and see what you can do. And like I said, we're going to go over them all together. So I'll give you another minute or two here to put down your thoughts. Okay, so it's been about 5 minutes. And like I said, I'm not expecting everybody to have all of them done. So let's start going over them. And then feel free to ask questions, as things come up. So as we pointed out, the link is going to be moving at 15 RPMs in a clockwise direction. So as we start here, the first section is going to be all W. So we're going to look at each one of the W's here with their letter and then determine, what the value is. So WA, or the angular velocity of point A. Point A is at the center of rotation or affixed to the frame. What would the value for W here be? Oh, Dylan said 0. Tyler, what did you say? 15 RPM. Anybody else have any input? David says 0. Virtually, does anybody? I'm going to put our chat box back out. Anybody virtually? Do you have what did you think W was? 0. Nia says 0. Brett says 0. Nicholas says 0. I agree with Dylan. Okay. All right. The answer is 0. Okay. A is considered the center of rotation, but it is not moving. Okay. So 0 would be A. Now, did somebody say something out? Well, if it's the pin, would it be rotating? Maybe. Okay. But A is still considered part of the frame. So it's considered that it's not moving. So we call that 0. Okay. All right. B, point B. Point B is on link 2. What would the value for angular velocity be at B? Danny says 15. David says 15. Nia says 15. I think 15 is a good number. Yes, 15 RPMs. Okay. With that same logic, moving to point C, angular velocity of C is 15 RPMs, right? Yeah. What about the angular velocity of link number 1, the frame?
0.
It's going to be 0. Yep. 0. The frame is not moving. Okay. What about W2? 15 RPMs. Yes, 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 yes. 15 RPMs. So those weren't too bad. And I think you could make a case maybe for A to be 15, but 0 is my number. Okay. All right. Any questions on those? All right. Now we're going to look at the velocities of the different points that we see here. So velocity of point A. And remember, velocity is going to be straight line velocity. Okay. So velocity of A, right there. What do we think? I'm hearing 0, 0. Virtually, what do you guys think?
Say 0.
0, 0. Tyler is a 0. Is that what you said? Yep. Okay. Yep. 0 is correct. link number 1 is the frame. It's not moving, so it has no velocity, correct. Or I'm sorry, A is part of link number 1, which is the frame. So it is going to be 0. What about point B? Point B is out here, right? Point B is on that rotating link. And it is going to be rotating, but it also has that straight line velocity component, right? Am I perpendicular here? I think I am. So point B does have a straight line velocity perpendicular to the radius back to its rotation, right? Okay. And we can calculate its magnitude using this equation. Okay. So what I'm going to do is I'm going to kind of draw a little thing here, and then we're going to go up here. We're going to say velocity of B is going to be equal to. So if we look at this equation, if I'm going to be the velocity of B is equal to W2, right? Because point B is on link number 2, so it's going to be W2 times radius to point B. And that radius to point B is the 4 inches. You see that from its center of rotation, okay? So we're going to be putting in here W2, right? Now, am I putting 15 RPMs in there? No, no. I need to convert it to whatever the number is, radians per second, right? So we'll do that work over here. So W2 is equal to 15 revolutions per minute. I'm gonna get this in here, I hope so. So I've got 1 revolution, 2 pi radians, and then I've got 1 minute, 60 seconds, right? That in there. Everybody see that? Revolutions top and bottom, minutes top and bottom, radians per second. So what is my W2 value? 15 times 2 times pi divided by 60. 1.57, is that what I heard? 1.57
Yep.
radians per second. So that's going to be the number that I use down here. So 1.57 radians per second times 4 inches, right? Okay. So my velocity at B, I think is like 6 point something. Is that right? 6.28. Anybody else get that? And
Yep.
I've already got units, inches per second. Are we in agreement? What happened to the radians? They what? They don't just disappear. They magically disappear. That's right. Yes. So there's our answer. That's right. They what? Oh, good one, Tyler. Yeah. 6.28 inches per second. Okay. Awesome. Any questions on that? Velocity of C. Velocity of C is also on that rotating link, and it's not at the center of rotation. So we're going to have a velocity of C perpendicular to its radius of rotation, which is 2.5 inches, right? So this is going to be RC is equal to the 2.5. And then the velocity of C, we need to find its magnitude. So if I go here, I can say velocity of C is equal to same link. It's on the same W2. So it's going to have the same 1.57 radians per second, but this time it's going to be the radius C, which is 2.5, right? So that's going to be equal to 1.57 radians per second times 2.5 inches. My velocity at C, what do we get for this one? Say it again, 3.93, right? And it's inches per second, just like we had last time, right? Units are inches per second. Good, radians disappear. So this is going to be 3.93 inches per second. Cool. Any questions on that? Okay. All right. We've got 2 more. Velocity of link number 1. 0, right? It's the frame. It doesn't move. So that's going to be 0. And what about the velocity of link number 2? We wouldn't say 0 because the link itself does not have straight line velocity. So we would say instead, not applicable, right? Just not applicable. Like it doesn't have that. It doesn't possess that. It only rotates. Okay. If you put 0, it's fine. But it's really not applicable because it's not even, there's not even an option for it to be anything, right? Okay. Questions? All the answers make sense? Cool. Then we've just got one more page. We're going to turn over one more time. Things to remember. Okay. Just fill in what you know about the items here. So equations for straight line velocity, units, direction, angular velocity, equation, units, direction. Make sure, just write your thoughts down and then we'll make sure you have everything that you need. So I'll give you a minute to do that. Okay. Straight line velocity. What is the variable for straight line velocity? I'm going to put that up here. It's the V, yeah, it's the V. Looks like this, right? That's the straight line velocity. That's going to be what we see for that. So the equations for straight line velocity, there's 2 of them. One for rectilinear, velocity is equal to distance divided by time, right? It can be d over t, it can be s over t, it can be r over t, but distance divided by time, where v equals velocity, d equals distance, and t equals time, right? What's the other equation for straight line velocity on a rotating link? Yep. So we have v is equal to w, or lowercase omega, times the radius, right? Where w equals angular velocity, okay? And r equals radius of rotation, right? Now, units for straight line velocity, what are the units we're expecting for them to be? I'm going to put in brackets the units. Tell me a set of units that we would want for velocity. So distance divided by time. So what distance divided by what time? Inches per second. What else? Meters per second. What else? Nope, not revolutions per minute. That's okay. That's okay.
Feet per second.
Feet per second. Anything else? Miles per hour, kilometers per hour, right? All that kind of stuff. Yeah. Okay. So anything that is distance divided by time. Could be centimeters per second. Did somebody say that? Yeah. Now, direction. Direction. It is always going to be perpendicular to the radius of rotation in the direction of rotation. Oopsie, rotation. Okay. Does that make sense? So if we go back to our first sheet here, our straight line velocities are all perpendicular to their radius back to their center of rotation, and they're in the same direction of rotation. So in this case, they're going down and to the right when we're going clockwise. Okay. And then we saw in this example, example 1, if we were going counterclockwise, we were going up and to the left because it's in the direction of rotation to be consistent. Okay. So perpendicular to the radius of rotation in the direction of rotation is the direction of straight line velocity. Okay. Angular velocity. What's our variable for angular velocity? That lowercase omega or W, right? That's going to be our variable. And then what's our equation for W? It's really a rearrangement of this one, right? Yep. Straight line velocity over the radius back to the center of rotation. Yep. Units for angular velocity. Yes, so revolutions, I'm going to expand it out here just so we see that. Revolutions per minute and radians per second, right? Remember, up here, in and out of that equation, it has to be radians per second. But we are going to be getting it, and we're going to be, if you would, delivering it in RPMs, okay? Direction, one of two ways. Clockwise or counterclockwise, right? One of those two. All right. So the next time we get together, we're about halfway through our handout. We've got 5 of 10 in our handout here, pages 5 of 10. So the next time we get together, we will start on page 6, which will be kind of a good review, if you would, as we come back. So Wednesday will be, we should be finishing up this handout, and then you'll be ready to finish the rest of the homework. Before we go today, what I do want to show you is the homework section that you do have the opportunity to do based on the information that we have. So what I'm going to do is I am going to go to first Module 4 practice problems. So what we've accomplished so far is we have that first example problem done from out of the book 6.1. And then we're about halfway through our handout, okay, which is a great place to be. So nothing to hand in yet for practice problems because we have to finish up our handout before we hand in. Now what we're going to do is we're going to look at assignment number 4 because there's a considerable amount that you can work on here. Actually, all the problems through 6.12 or 612, okay? So in your book, I think starting on page 161, if I remember correctly, yep. On page 161 is where the problems start for chapter 6, okay? So page 161 here. And the first problems that we have, 1 through 6, these are going to be that rectilinear velocity, okay? So these are all going to, or not all, but primarily that. So our first one here, it says a package is moving at a constant rate from one end of a 25-foot horizontal conveyor to the other, and it takes 15 seconds to do that. Determine the linear speed of that conveyor belt, okay? That is exactly like the problem that we did, example 6-1. Okay, that was the first problem that we looked at. So use that as your guide, and it's going to be velocity is equal to distance divided by time. 6.2, we have a hydraulic cylinder. It extends at a constant rate of 2 feet per minute. Okay, determine the time required to traverse the entire stroke of 15 inches. Okay, so you want to convert this to inches per second and then determine your time by rearranging that equation for t. Okay, easy peasy. And these aren't intended to be anything else but that. If you look at it like, is it that easy? Probably. Okay, probably. The next one, determine the average speed in miles per hour of an athlete who runs a 4-minute mile. So if we look at the rate, it's going to be 1 mile per 4 minutes. So if you take 1 mile per 4 minutes, this is just going to be a conversion to miles per hour. That's it. Okay. So it's just a conversion. Next one is determine the average speed in miles per hour of an athlete who runs a 100-meter dash in 10 seconds. Now you've got a little bit of conversion. So we've got to get miles per hour from 100 meters per 10 seconds. Okay. So there's a crossover from metric to English in the distance. Okay. The next one here is a gear is rotating at 270 degrees clockwise in 2 seconds. So it's 270 degrees per 2 seconds. You want to determine what the velocity, the angular velocity is in RPMs and radians per second. Okay, another conversion, honestly. And then the next one, determine the angular velocity in RPMs for the second, minute, and hour hands on a clock. So think about how many times that they go around in a unit of time, and then convert those all to RPMs. So those are the first 6 problems. Then the next 2 problems are 611. It says the drive roller on a conveyor, and it's this illustration right here on the next column, okay? Is shown. Determine the angular velocity W of the roller, okay? When the belt operates at 10 feet per minute. Okay. So if we go up here, we've got this illustration. So this is the belt. It's going on this drive roller. Okay. The drive roller is going in a counterclockwise direction. Now, to represent this in a kinematic diagram, kind of like what we've done in a couple other places, okay, you are going to show the center of rotation as a frame. Okay, that's going to be the center of rotation. So that's this point right here. You're just going to show a radius, okay, going straight up to the top. So in essence, this is the frame, and this is link number 2. Okay. Our center of rotation is going to be A. Yes. Oh, you can hand draw these. Yes, you can. You don't have to use CAD on these first ones. We will get to use CAD on the last problem. So these you can hand draw. And good question, Tyler. Thank you. Yeah, you can just sketch these, nicely. Okay, or use a straight edge. And then this is going to be point B up here. So kind of like our standard kinematic diagram symbology, but you don't have to draw that radius going around. Okay. Now it already told us in the problem that we have a straight line velocity here, right? And this is going to be the velocity at B of 10 feet per minute or feet per minute, right? I should put it top bottom, like I said. Feet per minute. Okay. And we want to determine what is W. Okay. So W2, the angular velocity of link number 2. Okay. Now they do show here that the diameter of this roller is 16 inches. So this distance from here to here is half of that, right? So this is going to be RB is equal to 8 inches, right? Okay. So with the information that we learned tonight, you should be able to find that. Now, you're going to get your W2 in radians per second, but you're not going to leave it in radians per second. You're going to give it to me in revolutions per minute, right? You got to convert it, okay? Now, problem 612, here we're going to have a drive roller in that same illustration. It's going to operate at 30 RPMs. How fast is the belt going to be going? Okay, so this time you're given W in problem 12 and you have to calculate V. Okay, so the setup is the same, but this time the velocity at B is going to be unknown and you're given W2. Okay. All right. So those are the first 8 problems that you have. I think then there's only 4 more. that we'll be then, learning about the next time we're together for you to finish up. Okay. All right. Any questions for this evening or for the information that we learned tonight? Okay. So then the rest of the evening you have to use as you so choose. So what I'm going to do is I'm going to stop our recording.